Okay, in this problem we have a focus on Newton's second law, both in translational and rotational form, and that focus is made through a apparatus that includes a pulley and a spindle and a spinning disc. So let's read the problem. So in a laboratory experiment, an apparatus is constructed that uses gravity acting on a hanging mass to pull a pulley that turns a spindle that turns a large iron plate resting on the spindle. So we see there's kind of a chain reaction here. The system is assumed to have no friction or other non-conservative forces, so we have simplified it in that respect. The hanging mass has a certain weight, which is given as 15.5 newtons. The pulley has a diameter and a mass, and we're going to assume that, we'll get to that. And the spindle has a radius and a certain mass. And then the disc on top has a radius and a given mass. And all the rotating objects are considered to be cylinders for the purposes of moments of inertia, so they all have the moment of inertia of 1/2 mr squared. Okay, so we're asked for one thing: what is the downward acceleration of the hanging mass? So we definitely want to have our add to our free body diagram here, show all of our forces. So as I said before, it's a simplified system in regards to having no friction or drag. And it's also a simplified system because we're assuming that our wire or our cord is massless. But what isn't simplified, and often is that we are not assuming that our pulley is perfect. We're assuming that our pulley has mass and therefore has inertia, and also we're assuming that the spindle that the platform rests on has mass and inertia. Okay, so that means that we'll have to consider them in our calculations. All right, so let's draw all of our relevant forces, and you can see that all of our diameters are clearly shown here, or our radii, right, and one diameter. Okay, so let's add to our forces. We have the force of gravity pulling downwards on the hanging mass. All right, we have a tension force acting up, and I'll label these in a second. Then we have a different tension force on the other side of the pulley. All right, so I will clearly show both tension forces, because that is the key thing to remember with non-perfect pulleys, or real pulleys, I should say, that because they have inertia, the tension on either side of them is different, because the very act of having inertia means that some of that force is effectively accelerating the pulley rather than just being transmitted through it. And we have a tension here. All right. So now let's start labeling them. So I'm going to call this tension, I'll call this one TS. This one will also be TS because that's the tension that's relevant to the spindle. Okay, because that's our spindle. Here I'll have TP and TP because that's the one we care about for the purpose of the pulley. And then this right here is FG. Okay, so those are all of our forces. So those forces are going to show up in sum of forces equations, and they're also going to show up in sum of torque equations. So let's collect our equations, which is a big strategy of this problem. All right, so what is that going to look like? So I'm going to have the forces in Y on the pulley. So change my pin size here. So the forces in Y on the pulley. All right, and that's going to be the sum of forces in Y on the pulley. I'm going to have the sum of torques on the pulley, and then I'm going to have the sum of torques on the spindle. All right, and yep, I was just checking out the mass of the spindle. Yeah, everything checks out. Okay, so let's write out those equations, and then really just kind of work through the algebra to solve for the acceleration of the system, because there's just the one translational acceleration. It's mentioned as the downward acceleration of the hanging mass, but it's also the translational acceleration of the at the perimeter of the pulley. It's also the translational acceleration at the perimeter of the spindle. But we'll see that actually in our calculations. All right, so I'm going to have positive y defined as, all right, let's do it this way. I'm going to just make the whole system move in the positive direction. Positive y here, positive theta in this direction, okay? And then positive theta in this direction. Okay, so like so. Positive theta. There we go. All right. So we have Fg minus Tp equals Ma. and positive ma because it's moving in the positive y direction, which we defined as downwards. Okay, then the sum of torques on the pulley, we will have, so TP creates a positive torque, so that would be TP times d over 2, right? And then it would be times sine of 90 degrees, which is just 1, okay? And then minus, so I'll just point out once that, that we have here, like so, sine of 90 degrees equals 1. All right, and then our other torque is going to be in the negative direction, and that's going to be TS multiplied by d over 2. Okay, and then that's going to equal the mass times the acceleration. So that's just going to be the, and that's the rotational mass with moment inertia. So it's just going to be 1/2 m pull times d over 2 squared. Okay, and that all looks great. All right, so now let's do a similar thing with the sum of torques on the spindle. So tau spin, well, that's just going to be TS multiplied by R. That's the only torque acting on the spindle. And then that's going to equal, well, here's the thing, it's actually going to equal 2 different moments of inertia, because we have to accelerate the spindle and the big disc on top, and they both have to accelerate with the same acceleration because they're connected to each other. They're rigidly connected by these struts, right? So when they accelerate, they're going to accelerate together with the same angular acceleration. Obviously not the same translational acceleration because it depends on where you are, right? There'd be a different translational acceleration vector here as compared to here, as compared to here, right? So, okay, but moving on. Right. So we're going to have, in parentheses, the 2 moments of inertia, so 1/2 m spin r squared plus 1/2 big M and then big R squared times alpha. All right. And then that reminds me that on my sum of torques up on the pulley, you probably notice I also forgot alpha because it's I alpha, all right? And this whole part right here is the I, so we obviously need an acceleration. Okay, and the other key idea that we're going to have here is that because there's no slipping in the system, all of our angular accelerations are exactly equal to the translational accelerations divided by the relevant radius, right? So divided by r. Okay, so that means, and so it's going to depend on exactly, it's going to be different for the spindle and the pulley. All right, so then what we're going to have, they have the same angular acceleration, but they won't have the same translational acceleration. So I'll write as 2 separate things here. All right, so here I'll write pull, and then r, and then this, I'll make this one a pull. Okay, so I guess the best way to think about it is that the translational acceleration, it's dependent on the radius. So they all have the same translational acceleration at their perimeter. So I'm actually not going to put a subscript there. But what is different is how that relates to their moment of inertia and their angular acceleration, because that is dependent on their radius. So I'll leave this. It's the one value of translational acceleration. Okay. All right. Okay. So, hold on. We have a technical issue here. Don't know what's going on. There. Okay. So, that one will be, we'll call this, so, yeah, so what is actually different, and I kept kind of coming back to the idea of what is actually different. It's the angular acceleration that varies between the pulley and the spindle. So, not between the spindle and the plate. They have to have the same angular acceleration, but it's between the pulley and the spindle. So so the subscripts that I need are going to be pull here and spin here. Okay? So then what's going to be different? Okay, so then what's going to be different is that I'm going to have alpha pull, and then we've been calling the radius of the pulley d over 2, just to be clear with our subscripts, and then we have a comparable equation, alpha spin, and that's going to equal a over little r. All right? And little r, not big R, and the big R is not relevant for the angular acceleration because it's not the big disk on top, this thing. It's just being moved with it. So it matters in terms of its inertia, but it doesn't matter in terms of the actual torques because it's not as if the string is wrapped around the perimeter of the big disk. Okay, so now we can just move forward with our algebra and solve for A. All right, so let's scroll up a bit. All right, so you can kind of see where this is going. All right, so at this point, it's just a matter of doing the math. All right, really, the biggest part is setting up these sum of forces and and making this connection like I did here. Okay, so we want to solve for A. We know Fg, right? That's basically our one known value. We don't know any of the tensions, so we need to substitute in for the tension of the pulley, and we do that with solving for the tension of the spindle. So we just kind of work our way backwards from here to here. Okay, so let's do it. And I'll make a little note there. All right, so like so. All right, so this is going to be the workflow. All right, so, oh, there we go. All right, so first step, solve for TS. All right, so the tension acting on the spindle is going to be 1/2 ms r squared plus 1/2 m big R squared, and then divided by little r. All right, and then that's going to be multiplied by the by alpha spin, which is going to be a over little r. Okay, like so. So we can see then that what's going to happen is this is going to cancel. We're still going to have the big R left in the equation, but we can clean that up a little bit. So we're going to have a over 2, which I'll pull out in the front, and then ms plus 1/2 mr squared. Okay. Yep, everything checks out nicely. Oh, well, it'd be r squared over little r squared if I want to do that calculation, the cancellation like I did. Okay. All right. So, oh, I see why I keep having the issue with the. All right, there. I kept bumping something, which is why you kept seeing on the screen the audio symbol. Okay, so no more of that. All right, so moving on, we're going to go work our way back up to the next step to substitute in the tension on the spindle into the equation of the sum of torques on the pulley. Right, so next step. So we'll substitute that in. So then I'm going to have Tp times d over 2 minus a over 2 times ms plus 1/2 big M big R squared divided by little r squared times d over 2 is going to equal 1/2 m pull d over 2 squared times a d over 2. Okay, so we'll go ahead and then want to solve for Tp here. All right, so you can see we're just going to move everything over to the other side and divide everything by d over 2. So let's think about where the d over 2 is going to cancel out. So that will cancel there and there. And then if I'm dividing by d over 2, this is going to become a d over 2 squared. All right, so I'll just add that. Okay, which then is going to cancel. All right, so then these two will cancel with this one. And let's see, because the little radius on the spindle, it stayed in the equation. So does it make sense for the half the diameter of the radius of the pulley to not stay in the equation? Let me just take a quick look at that. Yeah, so the best way to think about why d, or the diameter or the radius of the pulley completely cancels out, but the radius of the spindle doesn't, is this expression right here, r squared over little r squared, big R squared over little r squared, really represents the ratio of the two radii, of the actual spindle that is experiencing the torque, and then the big disc that's just sitting there, slowing down the system with its inertia. And so it's because it matters, it matters how relatively big they are. And so, as the ratio, approaches 1, then that's going to change. That's going to make it so that there's actually less torque required. When the ratio is really extreme, when little r is much smaller than big R, that requires more torque, and then it would also mean a smaller acceleration in this case, because that's what we're solving for. So it does make sense for a little r to not cancel out, whereas the effect of the diameter of the pulley does cancel out because there's nothing attached to it, and the torques are balanced in that sense, and the only thing that matters is the mass and the shape of the pulley. So the fact that it is rotational does matter, because notice the 1/2 does not cancel. So it's still there. Okay, so now let's solve for the TP, right? Or which is kind of the bottom tension on the pulley, because obviously TS also acts on the pulley. Okay, and so that's going to look like. We'll factor out at A. So then I'm going to have 1/2 M pull, all right, which I'll just call MP, because I'm already calling the mass of the spindle MS. Okay, and then, right, so that's factoring out the A, so that'll be plus 1/2 MS plus 1/2 mr squared over little r squared. Close it off. Oh, small parentheses, large parentheses. Okay. All right. Everything looks good, I think. Yes. Yeah. Okay. Factor. Yeah, because we have the extra 1/2. Oh yeah, because of the substitution above. Actually, the extra 1/2 is a mistake, because there shouldn't be a 1/2 there, because I factored out the 1/2 from here and here to get the a over 2, and then obviously that was the a. So yep, there should not. It did look out of place, and it was. All right, so I can move that in a little bit, and then do the same thing here. All right. So you can see that the expression then is like this. Okay, so now we're in good shape to actually solve for the acceleration. Almost, I guess. We still have a little bit of algebra left to do. So we're going to then substitute in the so-called TP, tension on the pulley, it's the bottom tension, into our forces. So we'll have Fg, which is just given to us as a force, minus A 1/2 MP plus MS plus, oh, still had a 1/2 in there. All right, plus mr squared over r. And here, let's write it as a ratio, right? Really call attention to it. So r over little r squared. Okay, and one more parentheses now. Okay, and then that's going to equal ma. Okay, we should solve for m. We weren't given it. We'll have to divide by g. Right, so it's going to be fg divided by g, because we're actually given fg in newtons. Okay, and so then solving for the acceleration, let's put all the acceleration terms on one side and divide them out. Okay, so I'm going to have acceleration, all right, and then I'm going to use brackets because I have so many things at this point. Okay, so the acceleration is going to be factored out of m plus, okay, and then so, oh, I see another mistake. I keep making mistakes in my algebra here. The mistake is really I left the 1/2 in the wrong place again, or in a slightly different way this time, because they all have a 1/2 on them. So in this step here, right? I had an a over 2 here, and I effectively had an a over 2 there, so that's what I factored out, not the a, by itself. So there we go. So, I make these mistakes, and with these type of problems, you kind of just want to look for it. If you see something that looks out of place, or just and just have some way to check your work. Just go back and look, and if it's not, it kind of seems like you have a, everything was a cylinder, so they should have a 1/2 on all of the terms. And if you don't, then it's definitely when you should go back and check, and then that's what I did, and I caught the mistake. Okay, so then m, so we factored out there our a, and so then we have a 1/2 MP plus MS plus big M R over R squared. Okay, that closes that off, and then bracket. Okay, looks good. And then that's going to equal FG, which finally gives us our final expression that A is going to be mg, just rewriting it, and then m plus 1/2 mp plus ms plus big M r over r squared. Close that off. Okay, looks great. And then we want to quickly find the value for m. So let's take a note and write that in here. So that m is going to be our 15.5 newtons divided by 9.8 meters per second squared. So that's going to equal, let's finally go to some calculations. We'll do a bunch here. Do them all in one swoop. So 15.5 divided by 9.8. So it's 1.58 kilograms. Okay. So now, scrolling back down, let's plug everything into the calculator and see what we get. All right, so in the numerator, we're going to have this value times 9.8, which I guess, oh, well, in that case, I can put just 15.5 in the numerator. So 15.5, all right. And then in the denominator, all right, so actually we don't need parentheses. So delete that. So 15.5 and then divided by, open parentheses for everything in the denominator. Now we'll put in this value. Okay, and then plus 0.5. Okay, and then open another set of parentheses, and that's this set here. All right, and then we've got the mass of the pulley. So mass of the pulley is 0.08 kilograms. So 0.08. All right. Now another plus. Okay. Open another set of parentheses. Okay. I guess we actually don't need that second set of parentheses, do we? Right? Because it's just, yeah, there's only addition inside of it. I think that really sort of persisted from when I had done the 1/2 above. Yeah, it's really a redundant set of parentheses, so we're going to get rid of it. All right. There we go. So there we have it. Much better. Okay. So then, continuing on, we have the mass of the spindle. Oh, I should get rid of it here too. All right, and it's good to show that it is a redundant set of parentheses because there I had one too few anyway, because it's we want to see that basically the acceleration of the system should have all of the inertias in the denominator. This is basically everything down here is slowing the system down. This is the one driving force, the gravitational force acting on the hanging mass, and it makes sense that this is exactly what we're seeing here. Is just the sum of all the inertias, with a very interesting result of here having the ratio of the masses because of that extra disk sitting on top of the spindle. Okay, so we had 0.08, so we're on to the mass of the spindle, which is given as 0.2. All right. So very light pulley, like a plastic pulley. The spindle's a little bit sturdier. Okay, and then plus, now the big mass. It's a whopping 5.8 kilograms, right? It's a big heavy disk. So 5.8 kilograms, and then multiplied by the ratio of the radii squared. All right, so it's big R over little r, so 0.24 divided by little r, which is 0.05, right? I'm obviously just converting things from centimeters to meters. Close the parentheses and square that ratio. Okay, and then that should be it for the denominator. So I think I have all my parentheses matched up. Okay, so let's kind of go through, make sure, double check. Okay, so that was big M times the ratio, 0.5 times everything that is rotational. Oh, I forgot it should be 0.08. So let's insert there. All right. Because like I said, it's a very light pulley. So there, let's fix that. All right. Didn't make a big change. And actually, it makes sense it didn't make a big change because really the system is dominated by that 5.8 kilograms. And we could actually see like what % error taking into account the spindle and the pulley actually makes on the problem here, which would be an interesting question. But we'll just wrap it up here with the acceleration that we originally sought to solve for. So 0.226 meters per second squared. All right. Well, thank you.